Hello, good people. Welcome back. We're still looking at, excuse me, the limit comparison test to see if we can find some way to determine the convergence of some maybe complicated looking series. I'd like to do number 6 and number 8 in this video, and then that'll kind of wrap us up here. When I look at number 6, I have to find a good series to compare this to, what I call my buddy series. Um, So I know it has to start like this, but what could I use? So looking at the rest of the series practice that we've done, I feel like we could ignore the plus two, I'm sorry. But then I have 1 over the square root of 3n, and I'm not really sure what to do there. So I think I might use this, which, if I rewrite it, is really this. And that's a p series, where n is equal, I'm sorry, where p is equal to 1/2, that's less than 1. So this is going to diverge. All right, so I'm going to take the limit that way, and let's hope everything works out. So the limit, as n approaches infinity, of 1 over the square root of 3n plus 2 times the reciprocal of this, which is the square root of n over 1. Okay. Well, this equals the limit the square root of n over the square root of 3n plus 2. And all of that is, I'm sorry, all of that is inside the square root. However, we know that the plus 2 is going to become insignificant as n goes to infinity. So we can say this is really the square root of n over the square root of 3n. And if that's the case, this is really the limit as n approaches infinity of the square root of n over 3n. And if that's the case, I can reduce the n's and I'll be left with the square root of 1/3. That is finite. That is positive. So therefore, the two series behave the same way. Well, my new series that I compared it to diverges, so therefore this has to diverge as well. Diverges because of the limit comparison test. So here's an example of, we found a series, we knew the outcome of this new series, that it was going to diverge, we did the limit, we found a finite positive value, limit value, so therefore the original one behaves like the new one that I found. Okay. When I look at number 8, that really looks complicated. So I have to think, what would be the buddy series here? Um, that's a good question. So usually we kind of shave off all the constants that are being added or subtracted. I'm actually going to keep that numerator. This becomes insignificant, so I'm going to focus on this, but I'm not going to use the 4. I'm just going to use n to the third. So how did I know to do that? I didn't. I'm going to try it to see if I can figure it out. But the idea here is it should be something that is similar to what I'm working with, right? And again, the plus 2, the insignificance of the plus 2 as n goes to infinity kind of leads me to believe I can ignore it. And the 4 as well, I'm going to ignore it. Turns out this is the same thing as 3 to the n over n squared. So what is going on here? This is not a p series because I don't have 1 over n to the p. And this is not geometric because I don't have just some number r to the n. This is a combination, right? Like I have kind of a geometric looking thing with a kind of a p series looking thing. But what I do know is that if I take the nth term test, if I take the limit as n approaches infinity of 3 to the n over n squared, which part, numerator or denominator, is going to get bigger faster? Well, the top is going to get bigger faster, so that's going to go to infinity. That doesn't equal 0, and if it doesn't equal 0, it diverges. That's what the nth term test does. It only finds whether it diverges, not whether it converges, and it's going to diverge if the limit doesn't equal 0. This doesn't equal 0, so I know it diverges. Great. So now I come back over here, and we're going to do a limit comparison test. Now that I know what this one does, I'm going to do a limit comparison test between the original nth term divided by the new term, the new nth term, which I guess I can do that. So this divided by that is the same thing as this times the reciprocal of that, right? Okie dokie, here we go. I can reduce the n's. I can reduce the 3 to the n's. I cannot reduce the n to the thirds because there's a plus 2 here, but at least it looks a little bit cleaner because now the only thing left in the numerator is n cubed. On the denominator, it's 4n cubed plus 2. Again, as n goes to infinity, the plus 2 becomes insignificant. So this is the same thing as the limit as n approaches infinity of n to the third over 4n to the third. The n to the thirds are going to cancel, and I'm left with 1/4. 1/4 is finite and positive. That means the limit comparison test can be used. So whatever the new series did, it diverged, is what the original series is going to do. So I can say that the original series that looks like this diverges by the limit comparison test. And we figured out the convergence, in this case, the divergence of this infinite series by using the limit comparison test. Comparison tests, not the first choice whenever you're trying to determine convergence or divergence. Try to see if there's another quicker shortcut rule you can use, like an nth term test, like a p-series, like integral test maybe, I don't know. But in the case where you can't, then we can compare it to a buddy series, something that looks like it and whose outcome we know, and whatever the original, whatever the new one does, the original one does as well.